This video is part of the periodic trends series, and it will focus on electronegativity. Electronegativity measures the tendency of an atom to attract shared electrons to itself. When we say shared, we mean that these electrons are already involved in a bond. So if you're looking at this picture of two individuals involved in a tug of war, and you recognize each individual as an atom, the rope that they're using for tug of war represents the bond between them and the electrons that are involved in that bond. So in this tug of war, the atom with the greater electronegativity value will more strongly attract the electrons toward it. One system of assigning electronegativity values is the Pauling scale. In the Pauling scale, the range of values is 0.7, least electronegative, to 4.0, most electronegative. So take a look at this periodic table with electronegativity values and see if you can spot the element that is the most electronegative on the periodic table. Did you find fluorine with its 4.0 value? Now see if you can find the element or elements with the least electronegative value of 0.7. Hopefully you found them in the extreme opposite end of the periodic table, francium and cesium. Notice that fluorine is a non-metal, and francium and cesium are both metals. Remember, nonmetals tend to gain electrons, and metals tend to lose electrons in order to achieve stability. If electronegativity measures the tendency of an atom to attract electrons to itself, then nonmetals, the elements that tend to gain electrons, should also have greater electronegativity values. Doesn't that make sense? Let's look at how the trend changes across the periodic table. When you go up a group, electronegativity increases. Take the alkali metals, for example, going from francium with a value of 0.7 all the way up to lithium with 1.0 as its value. Or let's take a look at the halogens on the extreme opposite end. Astatine, 2.2 is its electronegativity value, and going up the group, you'll notice iodine is next with its value of 2.5. Bromine is the next greatest with its value of 2.8, then chlorine 3.0, then fluorine 4.0. So because fluorine is the most electronegative nonmetal on the periodic table, it is also the most reactive nonmetal. So what causes electronegativity to increase moving up the group? Why does it do that? It's because the valence electrons are closer to the nucleus as you move up the periodic table. There are fewer core electrons. There's a lower shielding effect. The size of the atom is smaller. So because the nucleus is closer to those valence electrons, it can exert a greater attractive force on those outer electrons. Now let's look at what happens to electronegativity as we go across the periodic table. So electronegativity increases moving left to right across a period. So let's think about why that is. What happens to elements as you move from left to right across the periodic table? The number of protons increases. And because the number of protons increases, we say the effective nuclear charge, Z, EFF, that symbol represents the effective nuclear charge, exerts a greater attractive force on those outer electrons. Fluorine has 9 protons. It's in period 2. Lithium is also in period 2. They both have 2 energy levels, but it only has 3 protons. So because of fluorine's greater effective nuclear charge, it's able to exert a greater force of attraction on its valence electrons, pulling them closer to it. And it's also able to attract another electron in the process. Remember, fluorine only needs 1 extra electron for it to become stable like a noble gas. Notice the noble gases are absent from this picture. Think about why that is. Do noble gases want to attract electrons? No, they don't. So noble gases are the exception to this rule. When we are talking about electronegativity, you should exclude noble gases from this trend because they do not want to attract electrons. So you can consider their electronegativity value to be 0 or closer to 0. Let's take a look at a few of these memes to help us understand what's actually happening with the electrons and electronegative elements like fluorine. Fluorine's the most electronegative element on the periodic table. Its large nucleus with 9 protons combined with its small atomic radius, low shielding effect, allows it to exert a strong attractive force on its valence electrons. In addition to that, because it only needs 1 more electron to become stable like a noble gas, it will be the atom to most strongly attract electrons compared to any other element on the periodic table. So in this tug of war that's occurring here in this picture, fluorine is the element that will always win that electron. This next meme also deals with electronegativity, and it shows you part of a water molecule. So water, as you know, is composed of oxygen bonded to 2 hydrogens. So this picture is showing you part of the water molecule, this part right here that I've circled. So the red dot represents the oxygen, the more electronegative element. Oxygen is actually the second most electronegative element on the periodic table, second to fluorine. And the smaller white dot represents the hydrogen atom. So oxygen is pictured as the more massive atom because its nucleus is more massive. It's got 8 protons in its nucleus, and it's also got 2 energy levels. Hydrogen only has 1 proton. So the effective nuclear charge of oxygen is much greater than hydrogen's, 8 times greater, and therefore it will more strongly attract the electrons to itself. So in this tug of war that's occurring between oxygen and hydrogen over the shared electrons, oxygen will be the one to possess the electron for a greater period of time, you could say, because oxygen is the more electronegative element in this bond. Let's take a look at one more meme. So this one you've probably seen all over the internet by now. And this is showing you an electron right over here bonded to another or with another atom, belonging to another atom right here. And then all of a sudden fluorine walks by. Fluorine, being the most electronegative element on the periodic table, is going to undoubtedly attract this electron to itself. So that's why it says, how much electronegativity does fluorine have? The answer is just yes. Absolutely. This will happen. Okay? So hopefully you had some fun with those memes. Let's do some practice problems. Starting with aluminum and phosphorus, we're going to figure out which one of these two elements has the largest electronegativity. So pay attention to the wording when you're attempting these problems. Remember, the electronegativity trend increases when you go up a group and when you go to the right in a period. So electronegativity increases when you go in those two directions, with the exception of noble gases, don't forget. Okay, so aluminum is right over here, and phosphorus is right over here. They're both in the same period. So which one's got the greater electronegativity? Hopefully, you can see that it's phosphorus. Now, why does it have the greater electronegativity? They both are in the same energy level, so they have the same shielding effect. They have the same number of core electrons. So because they're in the same period, we then get to look at the effective nuclear charge. Aluminum has 13 protons, and don't forget, it's a metal. Phosphorus, on the other hand, is a nonmetal, and it has 15 protons. So it's got the greater effective nuclear charge, and it's going to attract those electrons to it. Next, we'll take a look at these two elements, argon and sulfur. So let's find them on the periodic table. Here's argon, and here's sulfur. So I circled them both in orange. Which one has the greater electronegativity? So hopefully you came up with sulfur as your answer. Did I trick you there? Remember, argon is a noble gas. Do noble gases attract electrons? Typically, no, they don't, because they already have full electron orbitals. They're already stable. They don't need to gain any more electrons to become stable. So sulfur is going to be the element that has the greater electronegativity. It's not about the effective nuclear charge. Argon does have more protons, but in this case, remember, argon is a noble gas, it's stable, and when we are talking about electronegativity, remember to exclude the noble gases. Next, let's take a look at carbon and nitrogen. So carbon and nitrogen, I'm going to use a highlighter this time. Here's carbon and here's nitrogen. I highlighted them in blue here. So which one of those has the greater electronegativity? Carbon has 6 protons and nitrogen has 7 protons. So 7 protons, greater effective nuclear charge. Nitrogen's the answer. Let's do one more. Magnesium and radium. So magnesium is over here. It's a metal, group 2 metal. And radium is also a group 2 metal. Which one of those has the greater electronegativity? Remember, electronegativity increases as you go up a group. Why? Because of the fewer core electrons. There's less of a shielding effect for magnesium, meaning the nucleus is closer to those outer electrons. Remember, magnesium is an energy level 3. It's only got 3 energy levels, while radium is an energy level 7. 7 energy levels. So radium has a much bigger shield compared to magnesium, keeping those valence electrons far away from the nucleus. For that reason, radium's nucleus, even though it is large, even though it's massive, even though it has a lot of protons, it's unable to attract, to pull in, to exert that attractive force on those outer valence electrons, pulling them in closer. It's unable to do that because the outer electrons are so far away. So distance of the valence electrons from the nucleus plays a role here. So for that reason, magnesium is the element with the larger electronegativity.